Okay, welcome, the brave few souls that have turned up today. And Meng Nang, thank you for coming in person. It's very much appreciated. This is the second time through of my lecture on electroanalytical techniques for clinical and biomedical investigations with the subtitle, Where Are My Molecules and What Are They Up to? I have a sort of reductivist approach to analytical chemistry. We obviously have to use statistics, and we'll use machine learning and tricks like that on whenever we need to. But in the end, I would much prefer a causal relationship between every signal I measure and the molecules and phenomena that I'm trying to describe. There's a selection of pictures on this title page. Okay, let's try sharing again. A college that prides itself in the high caliber of its engineering has tech that is not fit for purpose. So why can't I just click on one of these? Now it's popping up here. Yes. We're good. Okay. So, a selection of slides on the pictures on the front here showing some of the kinds of things I've worked on, starting on the top left with a bit of unlucky rabbit's foot that we were looking at the perfusion of tibialis anterior to look at transformation of skeletal muscle. Below that is a transparent fused silica cell that we grew cells on and able to look at their signaling with a zoom of that to the left below it, showing very happy primary endothelial cells growing well. Some microfluidic stuff, some microRNA detection using templated oligonucleotide templated electrochemically driven reactions, disposable sensors for point of care detection, some microneedles for therapeutic drug monitoring, and some modeling up on the top right using Hilbert transforms to extract data, particularly to be able to resolve closely related redox peaks, numerical modeling of collector-generated devices, droplet flow in microfluidics, and at the bottom right, an early experiment that we prefer not to talk about. What I'm going to be talking about today, if this wants to present, good, thanks. So, electroanalytical techniques, a brief summary. There's a nice review from Eric Backer's group, came out last year, that's well worth looking at. There are two broad approaches: potentiometry, which are essentially passive devices that can be described by thermodynamics and have a log linear relationship between the analyte concentration and the signal that you get out, which is the potential, typically for cations and anions, and we can also do ammonia and carbon dioxide if we couple these two enzymes. These have a very wide dynamic range, which is the upside of the log linear response, sometimes as many as 6 or 7 orders of magnitude, but limits of detection for the standard devices are around 10 to the minus 7, but can be extended to the picomolar level by putting complexing agents in the filling solution. And then in contrast to this, we have ones where we perturb the equilibrium potential or move away from the equilibrium potential and force a flux to happen at the electrode surface. And these are typically called amperometry, voltammetry, and coulometry. So amperometry, where we measure the current, the constant potential; voltammetry, where we have a potential program which we exploit to get analytical data; and coulometry, which is particularly useful in biological situations because we can integrate the current, take the noise out, which is always useful, the random noise out, always useful in a noisy clinical environment. But also because we cannot exploit Faraday's law. So if you know the volume of the solution that we've collected, if we count the number of electrons passed by integrating the charge, we can get the total number of moles in that known volume and therefore get the concentration without having to do calibrations. Limits of detection are typically of the order of 10 to the minus 9 molar at best, if you do well, 10 to the minus 12 with adsorptive stripping, which is comparable to atomic absorption and ICP techniques. There are also biosensors and point-of-care devices and diagnostics, which can fall into either of those categories, but I put these up as a separate category because they have an awful lot more engineering that has to go into these, but they're typically using bio-derived or bio-inspired molecular recognition, such as, for example, enzyme reactions, redox hydrolysis, or recognition using antibodies that we've generated and then created with hybridomas, aptamers, which is the latest game in town, using longish single strands of DNA, typically DNA, although RNA and proteins as well, but typically DNA of around 20 to 40 bases long, or even ion channels that we've cloned and cultured. And a sketch of the instrumentation required for both of these is up on the top right, but I'll be coming back to this in a little bit more detail. So what I'm going to try and cover in the next 2 hours, and it is ambitious, is really far too much. And some of the slides are here for reference purposes, and I'm going to not skip over them, but I'm going to mention the important points. But I would encourage you to read some of the text and definitely some of the equations. I thought last year, because I had 2 hours, I could talk almost indefinitely, and I've even added more slides this year and barely deleted any, so I think we're still going to be struggling for time. But I'm going to talk about the very idea of measurement in the first place. What it is we're trying to do and what needs to be thought about when we're measuring anything, and how we can assess whether or not our measurement techniques are fit for purpose. What are our figures of merit that we're looking for? And how do we validate them? The idea of using reference materials, standards for calibrating our measurements, certified reference materials in particular, approaches to calibration generally, and some ideas about error propagation, because you always see significant underestimates on these things being left out of most published data. And the reason for this is that when you do your error propagation calculation, it is typically a very disappointing result. It's one of the worst calculations. It's fiddly, it involves calculus, and the result makes you depressed and feel inadequate. And that's probably why people don't put this in. But it's absolutely vital if we're going to behave ethically and when we're describing our analytical techniques. I'm going to be coming back to what are the specific issues associated with either biomedical or clinical applications. Biomedical is when you're doing some research to support a clinical investigation, and clinical is when you're actually working with patients themselves. And the key questions, I think, is it working? Is my device even working? And how would I know if it was? So you have to be optimistic enough to try it out, but pessimistic enough to know that you need to check and do some validations. I'm going to sketch over a little bit about electroanalytical techniques. I'm going to mention the most important of these and comparison with other instrumental methods, and talk a little bit about potentiometry, the limit, how we define the limit of detection, its dynamic range and noise. In other words, the figures of merit that we need in order to assess whether our technique is fit for purpose. And in amperometry and voltammetry, a significant part of what I'll be talking about will be about selectivity and how do we detect the molecules we're interested in and only the ones we're interested in, and how do we quantify them. And biosensors, where we're coupling molecular recognition, and a little bit about pulse techniques. So the key ideas in doing any analytical measurement is that statement in red and underlined and shouty down towards the bottom right of the screen here, which is, how do I know I'm right? So in qualitative analysis, we're trying to identify the target and validate that somehow. But in quantitative analysis, we're going to be trying to get an indication of how many molecules per unit volume that we have here. And all measurements are subject to noise, so some sort of indeterminate error or random error. And all measurements that we report should consist of the central value, which is typically the mean or the median or the mode, but usually the mean, and some indication of the range within which the true value lies to a given probability, so typically 95% confidence limits. And if the indeterminate error is random, we can model this with Gaussian error curves, which gives us a bunch of statistical arithmetical tools that we can use. But otherwise, it may be more appropriate, if it's not Gaussian noise, to report the total range. If it's a handful of measurements, that's usually the right thing to do. Or the interquartile range, the middle 50% of the data might be more appropriate, and report the median or the mode. For most chemical and biological measurements, it's reasonable to assume random errors because we have so many uncontrolled sources of error in our experiments that they are effectively random. And the exception to this is trace measurement, because at very low concentrations, our lowest measurement is pinned at zero because we don't have any concept as to what concentrations below zero actually mean. So it might be best modeled by a log normal distribution at very low concentrations. Just drag this toolbar out of the way. So things we always need to think about when we're trying to measure something is, what is the question that we're trying to answer? What's the nature of the population of measurements that we're trying to take? What's the nature of the sample? And what's the form of our target analyte? and then we need some sort of statistical evaluation of the data. And then at that point, we might be in a position to attempt to answer the question. So I'm going to very briefly mention this kind of stuff, but what we're often doing is trying to is going to be quantifying the random error and then seeing, is there a significant difference between the measurement after we've made an intervention with our experimental subject compared with before. So we're wanting to know, is our experimental output more accurately represented by a single distribution, as on the left, or two overlapping distributions, as on the right, in which case, what is the probability that there is a difference between those means? And that's always what we're calculating. And I'm sure you've all covered this stuff before, and as undergraduates, and blanked it out of your memory the moment you passed an examination in it. But real noise is rarely white noise. It's rarely even power across all frequencies. It's typically dominated by electromagnetic pollution from power lines. It's frequently capacitively coupled, and you can see this if you do a fast Fourier transform on a background signal or a steady state signal, because you'll see that the fundamental is usually the strongest signal, which in the UK and Europe will be 50 hertz, and then there'll be a lower one at 100 hertz, then a higher one again at 150. And here's a figure, lovely figure from an ancient 50-year-old paper from Journal of Chemical Education, showing a kind of sketch, schematic of the power spectrum of a typical laboratory. So we see frequency, we see power over the annual cycle as the temperature changes, the daily cycle, the hourly cycle as people move around, every few minutes as somebody uses the lift, because electric motors are a major source of noise. Then they have 60 hertz in the United States, but it would be 50, 100, and 150. And here we've got the odd frequencies being at higher power, suggesting that this noise is capacitively coupled. And then on top of this, we'd have AM radio and TV, and then FM radio on top of this as well. But the actual frequencies need, when you're looking at the frequencies of the noise in your signals, you need to bear in mind the possibility of aliasing as well. Is your sampling rate high enough to get a true representation of the noise, to give you a clue as to where the noise is getting in? Because our starting point has to be to keep the noise out. And here's some data that we got with in a collaboration with Julie McPherson and the electrochemistry group at the University of Warwick. And this is what happens when you take your mobile phone into the lab. So on the left-hand side, we see the signal over I think it's around about half a second or thereabouts, of a 90 nanoamp signal being passed through a Hecker EPC10 USB current mirror. And we see those big bursts. And if we zoom in on the one on B, we can see what's happening here is your mobile phone is hunting for a signal, because you've taken your phone in the lab and not put it in airline mode, and you've compromised your data as a result of this. Now, why this is a problem in electrochemistry is the current voltage relationship in literally every electroanalytical and every electrochemical cell is nonlinear. And if you're close to the equilibrium potential, you'll have an exponential relationship between current and voltage. So if you apply a symmetrical signal to that, so even a sine wave to that, it will be partly rectified by this, causing your data to be offset. And what went into your cell as random noise is coming out as a bias in your data. So we published a tutorial review on the electronics that you need to understand to get the best out of your potentiostat. This came out in PCCP last year. It's a gold open access, so you can download this from anywhere without having to log on to your college VPN. And I've abstracted part of a table that we've got in there. I do recommend that you have a look at this review, because although the instrumentation, the analog instrumentation, is reasonably well covered in books like Bard and Faulkner and Heinemann, the digital aspects have not been brought up to date, and we put a nice big section there about the effects of sampling and filtering. But the kinds of noise that you get in your electrochemical cell that are going to degrade your signal, so power line noise, 50 hertz, and particularly the odd harmonics, switch mode power supplies, where if there's anything like fans or rotovaps, anything with motors, where the speed is being controlled, drills, milling machines, anywhere nearby, you're going to get big spikes from that. Any EM generating equipment, so fluorescent lamps like the Estates Department insist on putting in all laboratories. Ground loops from earthing your equipment at different points. You need to connect these through star earthing. So get a separate earth connection in your lab, get the estates department to put in a separate earth, which goes all the way back to the consumer unit, separate from the mains earth, so that you're not trying to use a main socket to ground your experiment, which is going to be subject to digital noise from all of the computers and phones in your lab. Poor connections are a real problem. Crocodile clips are an absolute nightmare. You should use gold-plated contacts because corrosive environment in a typical electrochemical lab where we're generating aerosols by bubbling gases through all our strong acids and saline solutions. You should clean your cables with ethanol before you start to dry them off so that you're not getting leakage currents that way. Try and have wet and dry shells so you keep the instrumentation above the lab and have a clean area where you can keep things wet. And definitely consider the impact that aerosol generation might have. Reference electrode resistance, blocked frits are a major problem. Always inspect your reference electrode, check the cable. Consider using a lug-in probe if you're working with non-aqueous electrolytes or passing large currents. And then stray capacitive coupling. So you use shortest cables you can get away with, use a Faraday cage and spread the cables out. These are all really good tips, and there are more if you go and read our tutorial review in PCCP about how to get the best out of your instrumentation and how it actually works. But here's some examples of what happens when you put your experiment in a Faraday cage. Benchtop is shown in red, Faraday cage shown in black in figure A. And we see there that because the sampling was happening at an integral multiple of the noise frequency, we're actually seeing this enveloping as well of the wave of the noise pickup, but you can see the noise goes down by about 3 plus or minus 3 nanoamps to barely detectable in a Faraday cage. When you open the door up on the top right, you see a burst of noise, and then close the door and the noise goes down by about a factor of 3. When you ground the potentiostat to the Faraday cage rather than to the mains, you get the black signal on the bottom left rather than the red signal. And if you introduce another instrument into the Faraday cage, such as, for example, a pH meter, you see the red signal in the bottom right curve here compared with the black signal in the absence of the pH meter in the cage. So these are all top practical tips about how to get the best out of your instrumentation. And there's now all these and more in the supplementary information and the main text of our PCCP potentiostat review. So all data are subject to random variation. Some is subject to determinant errors, which can arise from rectification, Faradaic rectification of a nonlinear signal when you put your random noise in. And you can also get gross errors. I put these in for completeness, which you can read at your leisure, but I'm keen to get on to the stuff that I can explain properly in person. And again, a set of definitions: precision, accuracy, repeatability, reproducibility. I've tried to follow the notation used by National Physical Laboratory and Laboratory of the Government Chemist, which they prefer a global summary of all of these things, typically a root mean square sum of all of these sources of variation, which they call uncertainty. And I've put this in for completeness, don't propose to go over this in detail now. Similarly, standard deviation, I'm not going to remind you what that is, but why it's really useful is it tells you what is the range of uncertainty of our central value. So it's plus or minus the standard deviation or some multiple of the standard deviation. More typically, for example, the confidence limits of the mean. How probable is it that the true mean lies within this relationship here? But one thing that standard deviation is really useful for is estimating the total standard deviation as the sum of the variances of the different steps in your analytical measurements. This is taking your sample in the first place, preparing the sample. For example, if it's a blood sample, you might be spinning it down. That's going to introduce random errors. And then finally, the measurement step itself. And if you can evaluate separately each of the individual contributions onto the right, you can say, where should I put my effort in order to make my measurement fit for purpose? And also it tells you, because we're squaring these, because the variance is what sums in your total error calculation, any standard deviation that's less than a third of the next largest standard deviation won't contribute to the overall variance. So you can also eliminate sources of error where you don't need to consider them. And we need to consider the most disappointing arithmetical calculation in science that I know, which is the propagation of your random error. The general solution is shown in this big equation at the top, which I think is sort of the diagonal of the Hamiltonian of your error matrix. So we're taking the square and we're squaring them up because they're random. So the absolute error, delta C, in your concentration calculations is the sum of the how does this measurement vary with each of the contributions to the noise in turn, summed as their derivatives multiplied by the typically the standard deviations, these delta X's, delta Y's, and delta Z. So we've got three, in this case, we're calculating a concentration from three different variables. These could be a dilution factor, a sensitivity factor, and maybe some other, and maybe a voltage that we get out of our final data. And all of these are going to be subject to variation. We want to know how the variations in each of these X, Y's, and Z's contributes to the uncertainty in our final concentration calculation. And this is the thing that you need to do. So this is often described in books and rarely given an example of, but I've got a worked example here from a ion selective electrode for calcium ion concentration determination, which is responding in a Nernstian fashion. So we've got this 2.303 to get us from natural logs to log base 10. So we're expecting in this case around 30 millivolts per decade in change in the voltage for every decade change in the calcium ion concentration. But if we have, and these are very optimistic noise figures working in a Faraday cage, maybe 0.4 millivolt standard deviation in the E0 value, 0.5 millivolts, and this would be good noise numbers. What is the resulting uncertainty if we're trying to determine calcium in the physiological range, which is very tightly controlled, from 1.15 to 1.3 millimolar? So the normal human plasma levels would cause a variation in signal of 3.2 millivolts. So even with these good data, we can see that we're going to get some big errors arising from this. So our starting point in assessing how these errors propagate in these situations is to calculate our central value, first of all, by rearranging the equation. And once we rearrange it, we can see how badly this is going to go, because we've got variations in slope, voltage, and offset, and they all appear in the exponent. Oh boy. But we get the central value, and then we need to evaluate the uncertainty of that central value. So we're only considering two sources of noise in this particular example: the noise in the voltage, the signal, and the noise in the offset of our calibration working curve, which is our delta, which I'm calling delta E naught. And so our variation, the square of our absolute error in our concentration determination, will be given by this equation in the middle. So we need to evaluate, we need to write down expressions for these two partial differentials and then sub the data into that. So we can see the dC by dE is ln 10 to the power E minus E naught over S divided by S, or with a minus sign in front of it, and a very similar expression for the for dC by dE naught. So we can sub in, we know the voltage we got for our measurement, we know E naught, and we know the slope of calibration. So we can simply sub in to evaluate these two partial differentials. And we know the variations in delta E naught and delta E. So we plug those in and we get this final 0.03. So we can see that our variation, the complete error expression, when we sub it in, we can see that our variation in concentration is 2.46 times 10 to the minus 5. So this is coming in at the second significant figure of our central value here, and represents a significant, and as I said earlier and repeatedly, a disappointingly large number, despite keeping the noise to sub-millivolt levels, which is a genuine achievement. What kinds of figures of merit are there in the analytical sciences, particularly as it applies to sensors and electrochemical measurements? What do we need to measure about our technique in order to establish whether or not it's going to be useful for our clinical partners, and whether or not we're going to be able to get MHRA approval or CE marking for our devices? We're going to need this as part of our quality management systems. We need to describe how our devices are going to work, if they're working satisfactorily, and we should really set up our target figures of merit in advance of running the project once we've established proof of principle of the device. So we need to have an idea of accuracy, how close to the true or accepted value we are, and we need some indication of the precision, how much variation in any one measurement is there, regardless of how accurate it might be. So we test accuracy with certified reference materials if they're available. So that's usually not the case in biology. So we might want to do comparison with reference methods. An example of this, one of my PhD students, Shulin Zhang, recently had a load of analytical measurements of, from condensed breath of lactate concentrations in patients that were exercising, or sorry, they weren't patients, they were healthy volunteers that were exercising. And then some of the numbers looked a bit odd. So we ran these against a mass spec determination, our sensor data, because any source of error that would cause our biosensor data to deviate from the true or accepted value is unlikely to contribute is unlikely to be the same source of error that would contribute to offset in a mass spectrometric method. So when we got good agreement between our mass spec data and our sensor data, we were greatly encouraged that the device was really working correctly. So that's a concrete example of why this is important. And to estimate the precision, you get a bunch of replicate samples, or you divide your sample up into multiple samples, and you do lots of repeats. We also need to know the response time, typically modeled as an exponent, where tau here is the time constant for the instrumentation and the sensor itself, which can be related to the 10 to 90% rise time, which is 2.197 of tau. So we can either use the time constant to characterize our rise time, our response time of our sensor, or we can use the 10 to 90%. As long as you report one of these, people who prefer the other measurement can calculate that one from the other. But typically, electrochemical devices are limited by diffusion, and the characteristic diffusion time is x squared, some representative distance, divided by twice the diffusion coefficient. Now, this x squared is typically the mass transport boundary layer. So this is going to be for example, the membrane thickness in a membrane-coated device, or it will be the concentration, the mass transport boundary layer calculated for a cyclic voltammetry, or it might be the convective, or some fraction of the convective boundary layer arising in a rotating disk electrode system. But how fast does your sensor need to be useful in biology? Well, in a normal human, adult human, the stroke volume of the heart is between 50 to 100 centimeters cubed. And if we have 5 liters of blood, we can quickly work out that to get a well-mixed solution is going to take around about a minute to a minute and a half. So we don't need to be any better than 1 minute in order to get an accurate representation of what your blood levels are of something. So temporal resolutions that are better than a minute are not actually telling us anything useful, apart from maybe mixing rates. But current bedside measurements, if you're doing it well and you've got good porters and you've got a well-equipped laboratory where the technicians and the research officers running the equipment are twiddling their thumbs waiting for a sample from you, might be able to turn it around in 30 minutes. So we can get order of magnitude improvements simply by having a sensor at all compared with the current situation. So it's definitely worth doing. What else do we need to know about? What's our dynamic range, or our working range? We get this from the calibration working curve, so a plot of signal versus analyte concentration. We have at the low end of this, we've got the limit of detection, below which signals are indistinguishable from noise, and we have an upper limit of linearity, above which the sensor stops responding or responds at with lower sensitivity. The slope of this calibration is called the sensitivity. The width of it is the working range, or the dynamic range. We should all, when we do our linear least squares, we should do some sort of statistical test on this to see, is it really linear? We usually don't have enough data points to test the residuals for normality, but a quick test that you can do is the sign test, saying, are we getting the expected distribution of positive and negative deviations of our values from our curve of best fit? The limit of detection is usually defined, according to the International Union of Pure Applied Chemistry, as the 3 times the standard deviation of the y-intercept interpolated on this working curve on the right-hand side here. So we measure 3 times the y-intercept, and we interpolate down to express this as an analyte concentration. This is telling us what is the smallest signal that's larger than noise. Limits of quantitation vary, or the definitions of this, but it's typically 8 to 10 times the limit of detection. Other things we might want to bear in mind is cost, but in clinical measurements, this is cost of goods is rarely an important factor. If you're going to be working in low to middle income countries or developing world context, you might like to look at the WHO assured criteria, which is published in this charmingly named journal, which will certainly change your browsing history, Sexually Transmitted Infectious Diseases in 2006. But it is really worth looking at, not just in the developing world setting, but how to think about how do you prepare a device for use by lay people, by non-experts. So I've mentioned that we should always compare our analytical results with some sort of reference method. ideally one that works on a different physical principle. How can we do this? Well, there are three broad approaches that are widely used. Paired t-tests, which can be done over a reasonably large dynamic range. You compare the differences of the results you get with your technique and the other technique. This assumes that the reference method is better. Regression analysis similarly assumes that one method is absolute, which is the one that we're plotting on the x-axis, and that you plot your new method on the y-axis, because you're assuming when you do least squares regression that errors only exist in the ordinate axis. And this may not be a reasonable assumption, particularly when you get down to the limits of detection. But there's a test called the Bland-Altman test, which is widely used in the field where it was developed, which is clinical sciences. But it's a really great way of comparing analytical methods, and I'm encouraging people to use this more widely when you're comparing one measurement technique with another. It makes no assumptions as to which method is correct. It's light on arithmetic, and I think it's also intuitive for most people to understand it. And it allows you to test for differences in sensitivity and bias, i.e. determinate error. So what you do is you plot differences versus means. So here's an example of a Bland-Altman plot down at the bottom here, compared with the regression line. So we've got two methods here, method A and method B. We can plot one against the other, and we're looking for the slope to be with slope of 1, or rather the confidence limits of the slope to include 1, and the confidence limits of the intercept should include 0, showing that both methods give the same result. So we've got a slope showing that actually method B is more sensitive because it's the slope is 1.06, varying between 1.02 and 1.09 according to the confidence limits. The calibration, the correlation curve does not tell you about linearity. It only tells you about correlation. So to bear that in mind. The Bland-Altman plot, on the other hand, does suggest we plot the differences versus the means over the entire dynamic range, and then best fit this. We see that there's a line here which is probably suggesting that method B gives systematically higher values at higher levels. So this is a really useful way of comparing analytical results, or indeed any sets of measurements where you're using two techniques. So I do recommend that you have a look at Bland-Altman method if you're not familiar with it, and look at this example in the slides when you get a chance. So when's he going to get on to the actual electrochemistry? Well, we're getting there. We're still talking about analysis here. How do we identify and quantify molecular species in biomedicine and in clinical sciences? We remember what it is we're after: concentration, how many moles per unit volume. Medics use really peculiar units. They often talk about the weight per unit volume, and they use funny units for volume as well. But we should encourage them to use molecular units so at least they can understand what's going on with their drugs. But what are the molecular properties that scale with concentration? Because these are the physical variables that we're going to be using to actually extract our analytical information. So intensity of light, you're going to use a spectroscopic technique. Mass, if we're going to use, for example, a quartz crystal microbalance. Gibbs free energy, which is what we exploit in our potentiometric sensors, because of there's a logarithmic relationship between activity and the partial molar free energy, which is the chemical potential, or more strictly the electrochemical potential. Or we can look at mass transport properties, which is what amperometric and voltammetric techniques do, where we're exploiting the relationship between the flux, which is proportional to the current, and some concentration gradient that we set up at our device. Or we can look at rates of reaction, like, for example, an enzyme-coupled reaction with a amperometric transducer. And then we can also consider specific quantitative reactions that our target is engaged in, such as reactions with enzymes, where we've had millions of years of evolution to get the selectivity, which we can then tart up a little bit more by doing some molecular engineering, or some sort of reactive polymers of some description, catalysts of one sort or another, and electrocatalysts. And I think I'm going to give some examples of these. Oh, but before we do, let's think about the specific challenges of doing molecular measurements in biology. This is by no means an exhaustive list, but if I'd known about this when I started my PhD, I think I might have moved into a different field, like process analysis or something, which was a better control problem. So to begin with, it's not even clear what concentration means in a biological context, because one of the many ways we know we didn't die in the night is that we're highly compartmentalized at every single length scale. every individual is different from every other individual within a population. Within a single individual, organs are compartmentalized one from the other. Within any organ, the cells are compartmentalized. You go look in the cell, you've got subcellular structures, you've got different gel phases, and we've got a handful of molecules at even reasonable concentrations. So here, 1 molecule per mammalian cell is picomolar concentration. And we know that we can't really think about concentrations in a mass action way without really having thousands or ideally hundreds of thousands of molecules in order to be able to do this. So this is a big problem that I'm not even sure I'm going to address at all, but we need to keep in our mind. We have, furthermore, also messing up our homogeneous solution, the fact that the molecules that we're interested in have very highly localized sources and sinks. So most of the molecules we're chasing are either from or consumed by enzyme catalyzed reactions, and enzymes are typically immobilized on membranes where they can exploit this phase partitioning that goes on between the lipid membrane and the solution surrounding it. And sampling is challenging. So here's an example from our own work from way back in the day. Before we started doing some sensor measurements on intact nervous system from the water snail, Limnaeus stagnatus, I thought we'd better have a look at see what's generally there. So we mashed up the entire nervous system and did a HPLC analysis using only electrochemical detection. So we're only going to pick up the electrochemically active materials. And on the left-hand side, we have the whole central nervous system, and we've got these 6 analytes that we were able to detect. 4 neurotransmitters, noradrenaline, adrenaline, dopamine, serotonin, and 2 of them metabolites, DOPAC, the breakdown product of dopamine, and 5-HIAA, the oxidative breakdown product of serotonin. And we see these different levels. But if we just looked at part of the central nervous system, the buccal ganglia, we see completely different distribution of concentrations. So even within the same organ system, we're seeing different concentrations of the same kinds of molecules that are fulfilling the same role in the same organ system. So this is already really complicated and why we needed sensors, but also why it's hard to interpret. All timescales are relevant in biology in principle. There are rapid dynamics in homeostasis and signaling, sub-millisecond vesicle release in neurotransmitters to minutes and hours for hormone release, for example, and very slow dynamics such as the processes associated with aging, disease, and death, which take place over months, years, and even decades. The concentrations we're chasing are very low. The more we improve our devices, the more we see that changes in concentration at even nanomolar levels are important. Some molecules are very tightly controlled homeostatically, such as, for example, the calcium example we looked at earlier, or pH, which is 7.2 to 7.4, and outside that range you are sick. And some molecules that we encounter all the time have very high dynamic range, such as lactic acid, or lactate, as it will be in a physiological pH, which ranges from sub-millimolar to tens of millimolar concentrations during normal activity. So what's normal? And trying to get a good control experiment is a major problem in biology. And then, on top of all of these problems, our matrix, that is to say, our sample matrix, the background against which we're trying to measure our molecules, is active, it's complex, and it's almost invariably moving. And we have spectator species, which are present in the background, whose concentrations are changing. Our presence of our sensor might cause some swelling or edema. And when the lymph is drawn into the tissue in response to provide this swelling, it's going to entrain small molecules with it and change the local composition, and also have some sort of flow. And homeostasis is a dynamic process anyway. So inflammatory and foreign body responses are going to change the chemistry and eventually destroy or encapsulate any implanted devices, deposit blood clots on them, for example. And control experiments are usually very difficult, particularly when you're working with humans. So these are all the reasons not to work in biomedical and clinical aspects of electrochemistry. The other thing we need to think about is, should we try and take our measurement on the fly in real time? Get real-time information? Or should we abandon all the phase relationships and take a sample away, analyze it at our leisure? So the advantages of measuring in situ, getting continuous or quasi-continuous data, can reveal biologically critical time-varying relationship. And the classic example here is luteinizing hormone in women, which needs to oscillate with a period of around 45 minutes. The mean value in infertile women compared with fertile women is identical, but you don't see the oscillations in infertile women. So if you take simple blood tests and measure a single value, you're going to lose that phase relationship. Another advantage is we can move our sensor close to the site of interest. So if we're looking for a marker for cancer, we can move it to nearer where we think the tumor is and get higher concentrations and drag our signal out of the noise. So any point of care measurements that we make might be able to do this not in an outpatient's unit or in a hospital, but in a more typical situation. So we're going to get more representative results of the biochemistry and physiology. Because you're sitting in an outpatient's waiting room, or you're lying in a hospital bed, you're stressed, all your hormonal levels and your basic physiological behavior is going to be completely different from normal life. And so what you end up measuring is not typical. The other thing is, if we want to do epidemiology and public health, or our advisors, we need absolutely colossal sample numbers. And we can only do this away from a hospital environment. And if we're taking measurements at all, this is because the clinicians have told us they want to act on this, and there is information that we can gather with our point of care sensor that can influence the clinical decision making, improve the quality of that decision, improve patient outcomes. Why would you want there to be a delay in that? And then finally here, another reason to do is therapeutic drug monitoring. We could use high therapeutic index drugs, that is to say, drugs where the ratio between a lethal dose and an effective dose is unfavorable, so you're not able to control the dose. Now, if you can measure the dose and the patient, in individual patients, you might be able to use, for example, antibiotics such as colistin, which is not recommended in most Western countries because of the risk of kidney damage, but it could be able to be used in, for example, cystic fibrosis patients away from hospital setting if you could do the therapeutic drug monitoring in the community. Now, the downside against all of these enormous advantages is you implant a device, you get a foreign body response, your sensor gets screwed up, and the biology gets perturbed. And even measuring on a sample look close to in a point of care device means that you're still getting a lot of interference from spectator species. Offline measurement here on the right is the wonderful Agilent suite in the Department of Chemistry on the White City campus. Tony Cast on the left, who was the early director of this, Alice Gast here. Look, and you see the size of these instruments. Yeah, these are terrific instruments, but they're expensive, they're capital intensive. You need top quality technicians and research officers running the kit. But the advantages are you've got time to clean up your measurement to minimize interference. These are well-established, validated methods, and you can do all of that stuff to characterize your chemical measurement step properly. You can implement quality controls really easily into your workflow. Downside is there are absolute limits on how many samples you can take from a human. This is a particular problem, for example, in taking blood from babies or newborn infants. You really can't get decent size samples from these patients. They're already ill. You don't want to drain them of blood before you and say, well, we could have cured them if only we hadn't taken all that blood out of them. We're going to lose all our phase relationships, all our time varying data. We're going to get analyte losses in the sample prep, inevitably, because you can never gain analyte. The high capital cost to get established means that it's unlikely that these measurements are going to be adapted in resource-limited settings or even widely adapted in developed Western economies where reimbursement can be a challenge for analytical device. And the requirement of technically competent staff provides an absolute limitation. And the data management costs are not insignificant. So still on the subject of chemical concentrations in biology, why do we bother at all? Well, the basic science is interesting. So concentration gradients and fluxes are fundamental to life. So if we can understand this, we get additional insights away from the more descriptive aspects of biology. Diagnostics, I don't need to sell anyone diagnostics after the last 2 years. But is there a cheap and easily measurable surrogate? Something we can measure that correlates with the disease state that we can use to replace an expensive and time-consuming medical history taking by a physician? Can we get a diagnostic that can be used instead? The key questions that we need to answer. The ex situ, this should be ex situ. Should we measure ex situ versus in vivo? How do we validate? Can we do standard additions or spike and recovery? And this should be done where possible. Can we exploit pharmacology to try and confirm our identification of our unknown analyte? or use the chemical and physical properties. Now, here are 3 examples at the bottom from some work we did measuring nitric oxide from around 1,000 primary endothelial cells that we grew on sensor arrays. And there's this peak at around about 0.9 volt, which correlates with nitric oxide concentration. Now, nitric oxide is important for signaling the growth of new blood vessels, so it's important in carcinogenesis and angiogenesis, where our cancers spread and metastasis, which is why we were interested. So we have a control experiment in the dashed line on the left. We added our angiogenin, we got an increase in this peak. Hey, we got more nitric oxide, but have we? So we put a control, we blocked off the production of nitric oxide using the methyl ester of arginine, so the precursor of the nitric oxide, and we knocked it back to control levels. So this showed that we were measuring something that was definitely related to nitric oxide synthase. But what was the rest of the peak? Well, we did some qualitative analysis tests here. So we extracted the culture medium that we're growing these cells in, and we hit it with sulfamic acid. Sulfamic acid reacts with nitrite, which is the oxidation product of nitric oxide. It reacts quantitatively with nitrite to convert it to nitrogen, which then bubbles out of solution and can't be detected. And we saw that a significantly large fraction was actually accumulated nitrite from the cells spewing out nitric oxide in the culture medium that we'd been using previously, because it was conditioned culture medium. So it already had nitrite in there, even though it wasn't put in when it was produced. So we were able to then correct all our concentration measurements by doing a check at the end as to how our selectivity. And a different experiment, different cells, this was central nervous system on the right here, also measuring nitric oxide because of its role as a neurotransmitter. And we were able at the end of the experiment to blow nitrogen through and remove nitric oxide because it's a gas. We could partition it back out into the headspace of the cell culture, or tissue culture in this case. And as we did this, in this case, the signal went right down, leaving just a small signal for nitric oxide. And this is because we were perfusing continuously. So these are ways that we can try and do validation in biomedical experiments, rarely capable of implementation in human experiments, but certainly in animal experiments and tissue culture. So we can use pharmacology, so known drug that manipulates the concentration, perhaps a selective reaction in the middle, or we can use the physical properties of our target analyte to manipulate it and see, are we measuring the thing that we think we are, and is our slope of calibration the same in our measurement situation as it is in our calibration steps. So I sum up all the problems of doing in vivo continuous measurement on this slide. This has been the bane of my life, and this has been a major part of our research activity over the years, even when it's only merited a paragraph or two in our papers, is what goes wrong when we implant a sensor in a human being. So I call this the WM3 problem, where the meat meets the machine. The interface. Outside, we've got biology we're interested in. On the other side, we've got our engineering, our current, our molecular recognition, our transduction, our current, our amplification, our op-amps, our digitization, our computers, and our signal processing, which we think we've got under control. But it's the interface between these two where things go wrong. What kinds of things go wrong? This is a color-coded slide. In red are the things that go wrong. In black is the consequences of what's going wrong. And in blue are suggested ways and workarounds with this. So adsorption is invariably going to happen. Proteins are always going to be, being amphiphilic, are always going to be happier at interfaces than they are in solution or in the bulk phase of a solid. So we get the consequence of that. It blocks diffusion to your electrode. You can get partitioning because the chemical properties of our interfaces change. This partitioning, because the proteins that are absorbing have fixed charges on them, so we can get Donan equilibrium, which is going to cause hydrogen ion concentration changes locally on the interface, which are not representative. And finally, this adsorption can deactivate catalytic sites. So on noble metals such as platinum or gold, electrocatalysis happens because these sites, these out of lattice atoms are typically reasonably promiscuous. They'll do anything to lower their free energy. They'll react with, they'll accept a pair of electrons from literally anywhere. You want that to be your target analyte, but it's going to be things like nitrogens on your protein, reduced nitrogens on your proteins, for example. Workarounds include working with new materials, biocompatible coatings, rigorous testing. Get your disappointment out of the way early. Test your sensor in 4% albumin solution. If it doesn't work in that, it definitely will not work in vivo. And if you measure the capacitance while you're doing this, from, for example, a hysteresis of a cyclic voltammetry curve, the capacitance will go down if there are things adsorbing on the surface, because you'll be displacing counterions in your double layer. So if we see the capacitance going down, we're seeing prima facie evidence, and we can get this independently of our analytical signal. How new materials work is up here on the top right, boron-doped diamond. This is a measurement of histamine in a cultured gut preparation. The gray lines at the top show there's an initial drop in the normalized current for the boron-doped diamond to repeated measurements, but it settles down and is reasonably stable over several minutes, whereas the carbon fiber electrodes that we've been using up until then fell and fell and fell and fell, and asymptotically approaching zero. We're going to get trauma when we insert our sensors. Here on the right, we can see in this pink H&E stained slide of tissue, we can see, you can't see my cursor, but this defect in the middle is where the sensor was. And we can see that there was about one cell distal from the tip of the sensor that was damaged. So providing our sample volume was large compared with that, we're mostly sampling from happy tissue. But what matters here is the size, the shape, and the location of the sensors. Another thing to think about is if your tissue is quite poorly perfused, is once you've inserted a sensor and a cable, you're going to be blocking blood vessels that used to be available for supplying that tissue. So bear that in mind as well. How can we be confident that we're right in such a complex media? So sensitivity and selectivity are important. We need to have good quality recognition chemistry, such as aptamers and enzyme reactions. We need to do some sort of cross-validation. We can perhaps manipulate concentrations that I showed on the last slide by pharmacology, or maybe even by spike and recover. We can locally inject our target analyte and see, is it still working? Or we may be able to do some fancy signal processing, and I'll give you an example of that later. We get a lot of noise. No one really knows how to ground a poorly conducting patient, where there are multiple paths to Earth, some of which are ohmic and some of which are capacitive. But wireless data is definitely the way forward, and Manos Drakakis, my colleague in bioengineering, who does a wonderful electronic design, amongst many other things, and did a nice paper with Martin Boutel where they showed that the noise on a wirelessly coupled sensor is so much better than when we've got cables. So good quality electronic design, talk to Manos Drakakis, consider wireless data at all times. And then the other thing we always need to bear in mind is, can we fish out a failing device? So if you implant a device, you know you're going to have to use surgery to get it out again. So you better be confident it's going to work. If you're going to mutilate a patient to implant a device, you can't just guess. You need to be very confident. Counter to this, it's worth bearing in mind that nothing works any better than electrochemistry. There's no such thing as non-invasive. So people work with fluorescent probes. Wonderful work going on over in physics, even now as we speak, on fluorescence lifetime imaging, for example. But adding a fluorescent probe to a biomolecule is going to change everything about its chemistry. Definitely going to alter its binding constant, and it's definitely going to alter the binding kinetics. How can it not? If you've ever you talk to a medicinal chemist, and they'll say, we can change the properties of this drug by replacing that bromine atom on this massive molecule with a fluorine, or replacing this carboxylate group with an ester. Changes everything. And we're supposed to believe that putting an enormous rhodamine on doesn't change the properties of the molecule. This is unbelievable. So maybe we can use radio labeling as an alternative to do some validations or checks, but we need to bear in mind that even if we use the most benign carbon-14 labeling, it's going to decay to nitrogen-14. It's transmutation. And this is going to leave unresolved valences, which are going to cause free radical reactions, particularly within cells, and damage to DNA. But even widely used probes in multiphoton imaging, such as the rhodamines and fluoresceins, can act as drugs. A paper that everyone really hates and tries to ignore in Science Signals, published, 3 years ago, showing that at the normal levels people use to do calcium imaging in the brain, the rhodamine 2AM and fluorescein 4AM at these normal levels cause depolarization by blocking sodium potassium ATPase. So this is actually depolarizing the cells you're doing the calcium imaging in. These fluorescent indicators are acting like drugs. So there's no way you can do any measurement. I mean, aside from Heisenberg, which we're never down to that level of noise, unfortunately, you're always doing something to your experimental system that's going to change something about it. And ideally, you should try and know what it is. So choose your artifact carefully and decide which ones you can live with. Where should we measure them? The traditional sources of samples are whole blood, plasma or serum. The traditional well-developed collection protocols, good interpretations, correlations with millions upon millions of samples that have already been analyzed. There is, however, a risk of infection. You've got a very limited volume. It's painful. If you're doing repeated determinations, you get tissue damage. And there's a risk of patient infection in bedbound patients if you introduce a catheter. Urine, another important analytical matrix, but there's variable delays. It's rarely acceptable to collect these samples in public, but we need some sort of control for the renal clearance in order to quantify our target analyte. So we need to take ratios, usually with creatinine, which is typically independent of the urine concentrations. But the analysis of all of these is typically lab-based, high-cost, capital-intensive. We need technical staff. There are significant delays, transport difficulties, and deterioration of a biological sample all the time between its collection and analysis. So here's a comparison slide of a bunch of different matrices: interstitial fluid, saliva, sweat, tears, breath. The research maturity in saliva interstitial fluid is reasonably high. Medium in exhaled breath. There's only, in exhaled breath, really only blood alcohol and H. pylori detection from stomach ulcers are widely used at the moment. But interstitial fluid, we've got some good ideas here. Saliva, the problem is the saliva production needs to be typically stimulated. It's not a controllable secretion. In tears, which are, again, cropped up a lot, but the dilution factor is around about a factor of 1,000, so you've got sensitivity issues. It's highly filtered. You can't get anything much above a few hundred Dalton. The time lag is unknown, and the composition of your tears depends on why you are crying. Composition changes dramatically if you've got something in your eye, a bit of speck of dust, for example, compared with if you're crying emotionally. So this is definitely an issue. But a nice review by Heikenfeld, which I recommend, from a couple of years ago, that gives a nice summary of all of this material. A little bit more here about analyte concentrations. Interstitial fluid I've put in a box here because we really like this, because it's very similar to plasma. Hardly any delays, maybe 15 minutes at most, depending on this. We're getting very similar levels from the work that Prasnitz has done using comparing mass spec data of the extracted interstitial fluid over a very wide range of analytes, going from ions all the way up to big, chunky molecules like cytokines and antibodies. Tears, I've already mentioned the problems with this, which is that the variation is just simply impossible to control for. And in any case, for glucose sampling, which is where people wanted to do continuous monitoring, the really major problem for type 1 diabetics is controlling their blood glucose at night when they're asleep. They don't want to go hypoglycemic, which is a life-threatening condition, while they're asleep. And you're not going to wear a contact lens in bed at night when you're asleep, so it doesn't solve the actual core problem. So again, somebody's not thought through their product design and development and their market analysis. Sweat, again, a problem. Typical rates are varying by an order of magnitude. There's a lot of intra-subject variation and inter-subject variation. There's a 2 to 5 minute lag from blood. And we need to have some sort of integrated sweat stimulation, because your composition of sweat depends on the sweat rate. So you're getting, if you're sweating passively, you're going to get around, for example, 4% of your blood alcohol levels in sweat. Whereas if you go into the sauna and have a really good sweat, you're going to be getting nearly 90% of your blood levels. So we typically have stimulation of sweat, either from a drug such as carbachol or pilocarpine to create sweating on that locally, or you have to heat it up, or you have to drag the sweat out with iontophoresis. But nonetheless, it can be made to work, particularly for ions. So here's an example of a pH sensor from a paper published a couple of years ago, NanoChem, a really nice device where they're getting good calibration working curves for an iridium oxide sensor, and they're able to see a decrease in pH from a patient that's running, but very little recovery during the rest period, interestingly. Continuous blood glucose monitoring. This just looks terrible, this graph on the right to me. I mean, this was put in as saying how well it worked, but I mean, I look at this and the Clark error grid in the middle here, and an awful lot of data, particularly in the region where we're interested in the hypoglycemia region. There's a really high chance that your data is going to be wrong when it's life-threatening. The actual specification for measuring blood glucose continuously, or even on a spot test, is 20% mean absolute relative deviation. So it's not particularly high bar to try and achieve, but it's set like this because this is as good as the technology is currently performing. So there's definitely a lot of room for improvement in these kinds of analyses. We've been doing a lot with interstitial fluid. It's the largest organ in the body. We want to try and measure in viable epidermis, this top pink layer here, where there are no blood vessels and no nerve endings. It's below the stratum corneum, the dead layer on the top of your skin, going to viable layer which is perfused by diffusion from dermis below it. So we've got no red cells, no clotting, and no nerve endings, so good patient compliance. And the compositions of interstitial fluid compared with plasma levels are shown in this table, which I got from a Journal of Applied Physiology review, 2011, showing really good agreement, except for albumin, where the albumin concentration is around a fifth of what it is in plasma. And this is a good thing, because this is what sticks to the surface of your sensor and ruins everything. So how can we access it? Microdialysis is well developed. It's FDA approved and CE marked. You can buy these commercially from a company in Sweden. It's used in brain trauma monitoring by Martin Boutel, my colleague, Professor Boutel, in bioengineering, in head injury and stroke. But you can insert it below the skin. It's not suitable for point-of-care applications, but for bedbound patients, it's a pretty good idea. But there are issues with the injury that it causes. The fact that actually it hurts quite a lot. How do I know? Because this is my arm on the top right-hand side, where we were comparing a fluorescence measurement with one of my sensors with a microdialysis probe and ultrasound to measure blood flow, all on my arm. And I honestly say, when the microdialysis probe was inserted, and it's a fairly chunky device shown in the middle here, pretty much near actual size, best part of a millimeter across. And the introducer, the device that's used to get it in there, is pretty chunky. It's larger than a millimeter. And I think if one of my students hadn't been with me, I might have cried when it went in, but I had to show stiff upper lip. Suction blisters are another way of accessing it. You know, just like new shoes or new hiking boots on an ill-advised hiking trip, you might get blisters where you get separation of the dermis from the epidermis. Causes these fluid-filled vesicles to form on the surface. We can then sample them, but you can't really do this long term. And reverse iontophoresis, where we pass a current through the skin, and ions will move, but they can't move without their water molecules, so you get a net electroosmotic flow, and this will then train other molecules in, which you can then analyze when you capture them at the cathode. But it does itch quite a lot. So itchiness, you've got to get patient buy-in with any technique. And there's a nice review of this from a couple of years ago in ChemSoc Revs with the reference shown here. Hollow microneedles can suck these out. These are beautiful devices from Prausnitz's group. I mean, absolutely beautifully engineered. They're really good for drug delivery, but maybe less good for molecular monitoring because they do tend to get blocked up. But the solid microneedle approach, developed by Tony Cass in chemistry at Imperial, I think the first paper was Anal Bioanal Chem 2016, look like these. The ones we've been playing with look like this. These are the engineering drawings on the left. The bottom and the middle is the polycarbonate, injection molded polycarbonate base, which we metallize over the microneedles with a patent deposition, and then functionalize that surface with some molecular recognition. And this is what it looked like in the early prototype, taped to, I think, Tim Rawson's left forearm, one of our clinical collaborators. So, on to how these work. I'm not going to spend too much time on this, except to explain where they go wrong. I'm summarizing how potentiometry works here. We're getting a signal which is directly related to the Gibbs free energy that changes when the activity of our device changes. We get an electrical potential, which scales with the partial molar free energy. In amperometry, we're applying some sort of potential that perturbs our equilibrium, and we get a flux arising from this, and we may have some molecular recognition linked with this, but we're basically measuring a rate of reaction. So here's what potentiometric data look like on, this is some iridium oxide sensors that we built on a cellular array. So we're growing, in this case, endothelial cells over the surface of these multiple sensors and getting reasonably good calibrations at the end of the experiment. around 77 millivolts per decade per pH unit compared with 59 for pH. And this is kind of what they look like in the middle under field emission SEM at the end of the experiment. This is a very busy slide that I use to teach undergraduates about potentiometry. I don't propose that we go through this now, but what we do need to think about is what changes with concentration is the membrane potential here in the middle. But what we measure is the whole cell potential. And we're hoping that the cell potential is only changing when the membrane potential changes, not when these two interfacial potentials in the filling solution and our external solution change. So if we fix the internal concentration, membrane potential will only depend on the activity in our external solution. So far, so good. But how do we measure it? Well, we got a sum of these potential differences between one electrode and the filling solution, across the membrane, which is the only thing that's affected by our analyte, and then at the external reference electrode, we have another interfacial potential. So what we actually measure is on the left-hand side here is our cell potential, but it's the sum of all of these things, and the second term is the only one that we have any real analytical relationship of. So when we do this experiment, neither of the outer terms on the right-hand side of this equation must change. So we've got to fix the interfacial potentials between the electrode and the solution on both sides of the membrane in order for this device to be analytically useful. So we need good reference electrodes here in shouty Twitter type text here. So the potential difference between the metal and the solution needs to be fixed and independent of the analyte concentration. I'm putting this in here because I work a lot with electrical engineers, for example, and they're not idiots, not a long way from, but they thought that the reference electrode potential was all about controlling the applied potential from the circuit. It's not. It's about controlling the interfacial potential in your device. So we're typically going to be using a silver chloride coated silver wire or a silver chloride ink or a calomel electrode. The calomel works better, but everyone's terrified of mercury because of its toxicity, so you're never going to get permission to use this on a human. So our silver chloride electrode exploits the solubility product, first year undergraduate physical chemistry, exploits this solubility product to predict the relationship between potential and which is controlled by the silver plus silver reduction. But because of this relationship with the solubility product, we can use this by fixing the chloride ion concentration. We can fix the silver plus concentration and therefore get a fixed interfacial potential difference. So we can lump these together. I won't go through all of these now, but the equation I want you to pay attention to is at the bottom here, is we need to fix this circled quantity here, the potential between the reference electrode Fermi level and the solution potential. And this must be maintained at a constant value, and we need to take the chemistry into account, and the chemistry that's described above here that gives us our Nernst equation with all our activity coefficients and so on needs to be a complete description, or at least a very good approximation of what's happening in our tests. So things to think about with your reference electrode. Is the ionic strength being kept constant? Is the temperature being kept constant? Has the chemistry changed in some way that's allowed our silver ion concentration to be affected? So, for example, proteins will form complexes with silver plus. Nucleic acids will form complexes and react, actually, with silver plus. So is there anything complexing our silver ion? Because that will change your reference electrode potential. Oh, and as 150 years of analog photography knew very well, all silver salts are sensitive to light. So you might want to bear in mind, should you do this with the light on or the light off? You certainly don't want to be doing it in conditions of variable illumination. But how much current can you pass with a 2-electrode cell? Well, use the Butler-Volmer equation to give you a reasonable answer. You wonder why you were always taught about the Butler-Volmer equation when you never actually use it in any real calculations when you hit the lab. Well, here's an example of where it's useful. So if we put in reasonable numbers for the transfer coefficients for silver plus of 0.5, and we know that the exchange current density out worst is about 1 amp per square meter, we can see if we want to keep the error below, let's say, 1 millivolt, which is not going to be good enough for potentiometry, but probably good enough for amperometry, then we need to keep the maximum current below 10 microamps if we're going to use a 2-electrode cell. But we can calculate, using the Butler-Volmer equation, a reasonable estimate of the error introduced by having leakage currents or even deliberate currents passing through our reference electrode. In potentiometry, calibration is a bit of an issue, and we need to calibrate fixing the ionic strength because we're required to assume that the activity coefficient is identical in all cases between our target analyte samples and our calibrations. So we use total ionic strength adjustment buffer. We construct a calibration working curve which goes from the Nernstian region down into a region where we're no longer getting any response, and we fit straight lines to this, and where these two lines intersect is called the limit of detection. It's typically around 10 to the minus 6 or 10 to the minus 7 in favorable cases. But work by Erno Prech at the tail end of the 20th century showed if you put a complexing agent in the filling solution, you can actually extend the limit of detection by another, well, in his case, 5 orders of magnitude down to picomolar levels. So what this does, what he showed here, was that actually what limits the limit of detection of an ion selective membrane electrode is typically leakage of the analyte from the filling solution. So I just mention this now in passing because often it's the simplest things. This wasn't thought about for the 50 years that these devices have been in use. But putting a complexing agent in the filling solution really improves the limit of detection. So here's some examples I'm going to go through now. We've been doing some stuff with antibiotic sensors for therapeutic drug monitoring and closed-loop control of the delivery of antibiotics. So we start here on the left-hand side with our penicillin, with our microneedle electrodes implanted. Oh, this is my hairy arm again on this one. Some bespoke electronics, a little bit of signal processing, and lo and behold, we get the answer that we want. The first sensors paper on this was published in ACS Sensors, only 3 years ago. Why is this an engineering problem? Well, antimicrobial resistance is an existential threat, certainly one of the top 3 threats to human life and health at the moment. Bugs have evolved resistance. Before antibiotics, around 2/5 of deaths were caused by infection, and life expectancy as a consequence is 20 years lower. So antibiotics have made a huge difference, but the development of resistance is a real problem. And we can see in this Department of Health document from the graph on the bottom here, how resistance is increasing. In this case, this is for gonococcal infection. So sexually transmitted diseases are becoming completely resistant now. This is in the UK. Gonorrhea is now completely resistant in many cases to any antibiotic whatsoever. But getting the dose right contributes to the development of resistance, because we get variations between individuals according to their age, their race, their ethnicity, their gender, any comorbidities, and any other medications that they may have. So, for example, once you're above the age of 7, you get the same dose, whether you're an 85, 90 kilogram professor or a slim, lissom undergraduate or postgraduate student, you're going to get the same dose for the same infection. That can't be right. On top of that, you're going to, during the course of an infection, which typically involves fever in a serious bacterial infection, you're going to get changes in renal function. So the rate of clearance is going to change. So here's the kinds of variations, coefficients of variation that you get in patients. So the amoxicillin, the most widely used penicillin on the left-hand side here, 40% coefficient of variation. Flucloxacillin, skin infection, the second most widely used antibiotic in the UK, 50% variation. So even in the most careful cases where patients are in hospital, around 2/3 of the patients are getting the incorrect dose, which if it's too low is breeding resistance. And it's breeding resistance not not just in the bugs that are infecting you, but it's also breeding resistance in your consomal bacteria as well in your gut. And because there's horizontal gene transfer between species, bacterial species, this is helping to get antimicrobial resistance out in the environment, whether it's happening in the patient or in the sewage systems or the sewage treatment plants subsequently. So this is definitely an engineering problem that we can address if we can control, if we can measure the drug concentration continuously in patients with through time, we can make sure they never get a dose that's too low to lead to resistance, and never get a dose that's so high that it's going to cause health problems for the patient. So this is what we need. We need measurement in subdermal tissue, ideally, to get some time measurement. which is then interpreted, fed through a closed-loop controller to an infusion device that tops up the dose and makes predictions based on the time dependency that it's getting from your sensor. The barriers to this at the moment are the timing of the samples, the stability of the samples on the way to the lab, getting them checked in properly, prepared, the analysis, the report, the review of the report by the prescriber, typically the physician, maybe in consultation with the pharmacist, some interpretation of this, adjustment of the dose, and by the time we get around this, everything's changed for the patient anyway. So what we need is some sort of sensor to feed a drug concentration, compare it with a set point, calculate the error, have a PID controller typically here that's then driving a pump that make predictions as to how fast the infusion needs to be to get the optimized dose, which is responding now to the unique patient's pharmacokinetics and pharmacodynamics. So the distribution, absorption, distribution, metabolism, and excretion by the patient, and whether or not the patient is even responding. So we use the solid microneedle electrodes developed by Tony Cass, originally for glucose monitoring, but this time we're putting a beta-lactamase gel on the top of this. So we start off with our base layer, which is injected molded polycarbonate. We coat this with conducting material, typically gold, upon which we then deposit iridium oxide by electrolysis. And on top of that, we put a gel layer of beta-lactamase, which is selectively catalyzing the hydrolysis of the beta-lactam ring in the penicillins, forming penicillic acid, which then dissociates, causing a drop in the pH, which we sense with our iridium oxide. And this is what the devices look like. These are beautiful ones made by Sally Gowes. We've got this nice tip area here with the lacquer below this and the hydrogel on the end here. And this is what a section of human tissue looked like after it came out, showing that there had indeed been penetration and the interstitial fluid had been accessed in a 20 micron section of human skin. The sensor is reasonably stable as long as you don't use it on the first day. 3 days in, 3 days in after we've stored it, it's giving reasonably good calibration working curves between for about 10 days, as when it's stored at -20 in the freezer. We think the drop in sensitivity is caused by washout, but it's good for a couple of weeks. Stable against sterilization. The green curve is the post-sterilization after it had been exposed to gamma irradiation from a cobalt-60 source, so we can make it sterile, so that's a relief. And we've got some plenty measurements now in healthy volunteers. This is, I think, Dr. Tim Rawson's arm. He's an infectious diseases physician over at the Hammersmith Hospital, currently working as a research fellow in the Center for Antimicrobial Optimization. And all of us had a little go at this, taking 5 doses of penicillin every 6 hours prior to testing, and then we left it overnight. So we saturated all our plasma proteins, and then we got 3 sensing surfaces in here, and we're also sampling blood, venous blood from a catheter, and we're also measuring microdialysis underneath the sensor to try and do a continuous validation. So we got our 3 sensor signals in green, red, and blue. We administer a penicillin dose, and around 20 minutes afterwards, we see the signals start to rise and then decay again as the drug is washed out. And in comparison with this, the microdialysis measurement showed that these were broadly tracking, and the blood measurement was slightly ahead of both the microdialysis and our sensor data. So we measured, and we got the venous blood samples analyzed blind using liquid chromatography mass spec by colleagues in the Department of Infectious Sciences, Infection Sciences in Bristol. And they also did the microdialysate levels as well. So they analyzed those blind, and we got those results back and plotted them against our sensor data. And still works after calibration. The sensors still looked like they were okay. It hadn't peeled the hydrogel layer off. 1 hour, a minute after infection, you see, after implantation, after it's been taken off, after 8 hours or so, you see a few marks that are more or less faded after an hour and completely gone the following morning. So the devices are well tolerated. We've seen no adverse reactions so far, and we get a pretty good agreement between the mean and the difference between the microdialysis differences on this axis versus the average of the two. And we're seeing that the overwhelming majority, particularly at the low concentration data, which is where this matters, we're seeing the vast majority of the data agreeing within 1 plus or minus 1 95% confidence limit at the mean. So we're pretty pleased with all that. Moving on to amperometry. I don't propose to revise stuff that must have been done earlier on in this course, but we're imposing a non-equilibrium potential which causes this ratio in the Nernst equation to readjust itself so that the voltage is now correct. The equilibrium concentrations here now reflect the potential that we've imposed rather than trially measured. And the rate at which this happens depends on a potential dependent rate constant, typically interpreted in this kind of empirical Butler-Volmer kind of way. I'm going to skip through these because I think we've already had this somewhere else, and move straight on to just remind you what you need to be able to do in all of your experiments is to stabilize the concentration boundary layer at your interface, because that is what is giving you your signal. So your flux, the rate of mass transport, which is equal to the rate of any reaction that's happening at the surface, is the current divided by Faraday's constant, the area of the electrode, and the number of electrons transferred. So the concentration gradient at the surface is the critical parameter that needs to be stabilized either by having a membrane or well-controlled mass transport at the surface. And we can characterize this. This is typically then, the mass transport rate constant can be understood as the ratio of the diffusion coefficient to the Nernst layer thickness, or the mass transport boundary layer thickness. And this, at the bottom here, we're seeing then our limiting current, in the case of a diffusion limited reaction, is equal to the mass transport rate constant times the bulk concentration. This falls out from this boxed quantity in the middle here, which is the external current that we measure divided by Faraday's constant, the area, and the number. So we're getting a proportional relationship between our current and our target concentration, a linear relationship here. And if we don't stabilize our Nernst layer, either by forced convection, a membrane, or making our electrode tiny, then we're just going to be subject to all kinds of noise variations, vibration, density gradients, and so on, perturbing this concentration gradient and giving us random signals. Microelectrodes work because we can hide our concentration boundary layer within any natural convection boundary layer, and a reasonable value for the natural convection boundary layer in a typical laboratory experiment with no controlled convection. So this is what arises from temperature gradients and diffusion gradients in a normal sized beaker in a normal laboratory, is around about 0.05 centimeters. So as long as our characteristic length from diffusion is small compared with that, then we're going to be able to get reasonable responses from our sensor. Experimental setups, I'm pretty sure, is well known about. Just going to mention counter electrodes, the thing everyone forgets. Two things to bear in mind about counter electrodes. First of all, it needs to be large compared with your working electrode, because we need the current through our cell to be limited by the reaction at the working electrode. And remember, what's happening at the counter electrode is typically solvent electrolysis. So we're typically going to be decomposing the solvent, either reducing it or oxidizing it. These are reactions that you normally have to have a lot of electrocatalysis to make them work well. So we're relying on that being able to supply any current that the working electrode needs in order to do this. And we can only be confident this works if the counter electrode is large enough to do this. Surprisingly, this is not the case for many commercially available screen printed electrodes, and you might want to bear that in mind when you make your purchasing decisions. Secondly, there is an electrolysis reaction happening at the counter electrode, which is definitely changing the local pH. If you're doing a reduction reaction at your working electrode, you will be oxidizing the solvent at your counter electrode and decreasing the pH. That may not matter, but you definitely need to know this. Conversely, if you're doing an oxidation reaction at your working electrode, your counter electrode reaction pH will be going up. And if you're trying to do long-term measurements over days in an implanted device, you definitely need to think about this, because you're going to be getting high pH regions that are going to hydrolyze the tissue around the counter electrode and possibly cause extensive damage. So what we want to do is what's written in red and underlined in the middle here. We want to make sure that our cell current is limited by the electron transfer reaction at the working electrode, or by mass transport, ideally, to the working electrode, which is going to control the electron transfer reaction rate. The instrumentation, this is covered really well, I think, in this paper that I wrote with Julie McPherson and Alex Coburn and Katie Levy. Why I've put this circuit diagram up, because as you can see, if you from your undergraduate op-amp lectures, you can see if you disconnect your reference electrode first, you're going to apply the mother of all voltages to your counter electrode. And this is going to drive a colossal current to your working electrode, through your working electrode, which is held at virtual earth. So when you're assembling and disassembling the cell, make sure the reference electrode is always well set up and in good condition to stop you from destroying all of your delicate recognition chemistry on the working electrode when you power it up. So don't disconnect the reference electrode. Always disconnect the working electrode first and connect it last. Maintain your reference electrode fritz and check your filling solutions. So top advice. Where does the selectivity come from in our amperometric devices? Well, number one, potential control, because this is tuning really the Fermi level of our electrode to the molecular orbital levels, either highest occupied molecular orbital or lowest unoccupied molecular orbital in our target analyte, and the solvation energies associated with these redox changes. So, for example, on a gold electrode, if we power it up to plus 0.8, we can measure nitric oxide. Minus 0.5 volt, we can measure dissolved oxygen. So all we need to do, we have the same device measuring a signaling molecule, nitric oxide, and a metabolic marker such as dissolved oxygen on the same sensor, on the same cells, just simply by switching the potential. We can have selective membranes, make them gas permeable, for example, or we can have molecular imprinted polymers to do this, or we can engineer the surface in a more sophisticated molecular recognition using antibodies, aptamers, or enzymes. And then finally, we can operate these at steady potentials to do amperometry and coulometry, or we can apply potential programs which reduce the analyte consumption to make sure our sensor is not eating any more of the analyte than the tissue, which is always a good thing. So we're not competing or perturbing our biology. So this can improve the sensitivity and limit of detection because your concentration gradients are steeper at short times. And so this might drag your current out of the noise and improve confidence in qualitative analysis by looking at the current voltage relationship and identifying peak potentials. And the important voltammetric techniques include cyclic voltammetry, differential pulse voltammetry, and square wave voltammetry. What kind of molecular recognition chemistry can we have? Well, antibodies, but they ultimately boil down to this equilibrium reaction here, which is described by an equilibrium constant called the dissociation constant. And so this is going to have units of concentration, and good numbers for that are 10 to the minus 12 to 10 to the minus 9 molar. But it's typically micromolar to nanomolar concentrations. If we're wanting to detect picomolar and nanomolar concentrations, this is how good our binding and dissociation constant data needs to be. And the box here on the left shows how these antibodies are actually made, but we're normally buying these things in. Aptamers are nucleic acid single strands, or sometimes RNA, but typically DNA because it's chemically more stable, of 20 to 40 bases long. The binding is determined by the tertiary structure, and the target recognition involves some three-dimensional conformational change, relying on hydrogen bonding and hydrophobic interactions, base stacking, and intercalation in hairpin regions. So they're more stable than antibodies. They can bind to small molecules without having to have conjugation to a protein. And because they're chemicals, once we've identified an appropriate aptamer by selection, we can sequence it and we can make these, or get them made at very good cost with comparable binding or dissociation constants to seen by antibodies. The way they're selected is by this Celex process. So you have your target analyte, sometimes bound to the magnetic bead, for example. You drop it in your target analyte solution. We have a random selection of around 10 to the 14 different sequences of DNA in the solution. Some of these will bind to our target. You fish your magnetic bead out again. You wash more or less rigorously to identify the ones that strongly bind. Then you amplify them by PCR, and you then go around the process again and again until you get reasonable figures of merit for the binding constants, until you get down to submicromolar by dissociation constants. So this is how we get them. When they bind the target, we get conformational change. This may cause a mass change, so perhaps we could do this at QCM. Surface acoustic wave will change, but typically we're going to be exploiting in electrochemistry a redox marker that we've stuck on the distal end, most usually methylene blue, although that is a nightmarish redox chemistry, and I would encourage anyone who's interested in this to think about how we could develop better redox reporters. But what's happening here is if we get a conformational change that shortens this chain length, then the redox active group at the end of our aptamer chain is going to be spending more time in the vicinity of the electrode, and this is going to increase the first order rate constant that we would associate with the electron transfer reaction, causing an increase in peak current that we see here on the right for a sense of it for the antibiotic kanamycin, where we get amplification over the background current because the methylene blue is at the end of this aptamer, when it binds our target, is spending more time close to the electrode surface. And there's some reviews here if you want more background information on this. Molecular imprinted polymers are another way we can go. I've done a little bit in this. I have to say I remain skeptical despite having published some of this. I think the bigger the molecule, the better you get, and conducting polymers have something good to do with it as well. So what you do is you've got some monomers, and here we've got a mixture of some deoxythiophene, and we let these hydrogen bond to our target peptides, and then once we've done that, we polymerize on the electrode surface, and then we wash our target out, and we should have target-shaped holes on our electrode surface as a result of this. And we get some reasonable numbers. In the case for alpha-synuclein, which is a biomarker for Parkinsonism, we got some okay-looking data, which we published a couple of years ago. We can also exploit selective reactions, such as, for example, Prussian blue, for detecting hydrogen peroxide. We've got our second clinical evaluation going on with this setup at the minute, with some patients down at the National Heart and Lung Institute, so I'm very happy with this stuff. And this is hydrogen peroxide reacting catalytically with nanoparticles. You can see these cubic-shaped crystals of Prussian blue embedded in a conducting polymer film of so polyethylene deoxythiophene polystyrene sulfonate, which then conducts the charge to the electrode surface. We engineered this to make it limited by analyte diffusion within the polymer film, and we can run this at really low potentials for close to 0 volts, where there's good selectivity against oxygen, and we're getting limits of detection well below micromolar, which is certainly in the target range that we need. We're getting so 2 to 10 micromolar concentrations in patients with COPD. Micromolar concentrations in the breath of volunteers who've just had a cigarette, and submicromolar concentrations in healthy individuals who had no cigarettes, no smoking. So we're getting some nice data out of this, so this definitely works. Just simply using the very selective reaction between hydrogen peroxide and Prussian blue. And finally, another recognition chemistry developed originally by Sylvain Ladame, a colleague of mine in the Department of Bioengineering. We published something here where we're looking at target for microRNA as a biomarker for prostate cancer, published a year or so ago. MicroRNAs are a new class of biomarkers if they hybridize with 2 peptide nucleic acid probes. So here are our probes at the top here on the left-hand side. At the blue one, at one end, we've got a catechol molecule. So 2, this functional group here shown in the box. And on the other end, we've got an aniline. When they bind to the target, microRNA, by hybridization, it brings these head groups closer together, increases the rate of reaction. And the reaction is switched on under electrochemical control by oxidizing the catechol moiety to the quinone. And once it's a quinone, it'll undergo a selective 1,4 addition reaction with a nucleophile, in this case, the aniline. So in the first scan, the cyclic voltammogram, in blue, we see a nice big peak for the catechol oxidation, which can now that we've formed the catechol, it can react with the aniline. And when it does so, it forms a new redox active group, shown in red on the bottom right-hand side of the middle voltammogram here. And we see the voltammetric behavior in the middle of this arising from this. And if we look at pulse voltammetric ones, we see the catechol peak going down with increasing target RNA and the adduct peak going up. So we can take the ratio of these and get a kind of internal referencing. The bottom right shows after the data has been well and truly diddled around with, we can see that we've got a dynamic range over, well, certainly 2, close to 3 orders of magnitude, going from 10 nanomolar up to 1 micromolar concentration. Finally, we can exploit enzymes to do this. Here's an example, lactic acid. We're interested in lactate because it's a really important validated biomarker of sepsis. Sepsis has a lethality of between 60 and 80%. Young people are at a bigger risk of dying as the elderly in this, from random infections that just become systemic. The symptoms are rather general. So you turn up at your doctor with a little bit of fever, lassitude, a little bit of pain and inflammation. This could be anything. Could be a cold, could be COVID, or it could be sepsis, and you could be dead within 12 hours. If they could measure your lactate in the community, you would get an indication, high lactate levels. Certainly if it's above 2 or 3 millimolar, but definitely above 4 millimolar, it strongly correlates with mortality. So if we could get some devices out into the community, it would be a really important differential diagnosis where there is a definite action the physician can do. They can give you a broad spectrum antibiotic. If you come in with a fever, they think it's influenza or COVID or a cold that's got a bit out of hand, they test your venous blood lactate levels. If that's nice and low, fine, they just send you home and tell you to grow up and show a little bit more self-control. If on the other hand your venous lactate levels are high, you're probably going to go into sepsis with a really high risk of death. They can give you broad spectrum antibiotics intravenously on the spot and then send you into A&E or into a high dependency unit or ICU to get looked after properly. So there's actually good outcomes that would improve patient care. How do we analyze this stuff? Oh, I'm a big proselytizer for Kutetski-Levitch analysis. I know rotating disc electrodes have gone seriously out of fashion, but nonetheless, this is a very robust way of getting really good data about the relative rates of, and even absolute rates of every single step in this reaction. So we've got some target substrate, could be our lactate. It reacts with enzyme, lactate oxidase, for example, to produce pyruvate. The enzyme is reduced in that process. It needs to be reoxidized by some mediator, which in turn is reduced, and then we oxidize the mediator at our electrode, and we hope that the rate of charge transfer on the right-hand side of this top figure is correlated with the rate of mass transfer in the external solution, and thus our target analyte concentration, because our rate of reaction is always going to be the current divided by NFA. But we can, if we make a reciprocal sum of this, and by analogy with Ohm's law, what we're actually doing here is summing the resistances, the resistance to flux in the solution, the resistance to membrane mass transport, the second term in the equation at the bottom, the resistance to reaction with the enzyme, and the resistance arising from the enzyme mediator reaction, and finally the resistance or charge transfer resistance arising from the mediator reaction with the electrode. Oh, a bunch of equations. Even at this range, with relatively few of you online checking this out live, I can already feel the alienation levels rise with all these equations. But let's look at these in turn. We can get the solution current directly by changing the rotation speed in a rotating disc electrode. Or if we want to get higher rates, or we don't have an RDE rig, we can use different sized electrodes, microelectrodes, and look at this and plot these out as a function of 1 over the current here will give us 1 over the electrode radius. So if we have multiple sized microelectrodes, we can determine this. And best of all, if we look to the bottom right, these are real data collected by Shuli and Zhang. We're getting straight line relationships for this first term. We know what this should be at a rotating disc. We know what it should be at a microelectrode. So we can check, one, is this linear like the analysis is predicting? And if we're getting a straight line, we're believing our data because we know that we're doing the experiment that we thought we were doing. Secondly, we know what the slope should be. In an RDE, it's the Levitch slope. And a microelectrode is 4NF-CDA. So it's going to be 4NF-CD is going to be our slope at a microelectrode. Of each of these in turn, as we change the electrode size or look at different potentials. Then we can load the enzyme. Then we can look at the diffusion limited current, just the diffusion limited current alone. And this means that this term, by looking at the intercept, at the zero intercept, our rotation speed is infinite. So we've got infinite mass transport at this intercept here. So our intercept value is going to be the sum of all of these remaining terms. And as long as these are all high, we've engineered this to get our enzyme concentration high, we've got rapid kinetics of our mediator, we can now characterize the mass transport rate constant of our membranes and optimize those. So from the intercept, we can get the mass transport rate constant multiplied by the concentration. And yet again, we've got a way of checking, is this reasonable? We change our analyte concentration. If the intercept concentration changes in the same way as our concentration changes, we know we've done the experiment right, and we can get our mass transport rate constant from a slope. We then measure the thickness, and we can maybe get estimates of the partition coefficient, and we can even get that way the diffusion coefficient of our membrane. Then the next thing we can do is we can change our enzyme concentrations, having optimized our membrane properties. And we can start backing out K2, or K2 over Km rather, which are our enzyme properties, and tell our enzyme manufacturers, have they optimized our enzyme properly? And then the remaining terms, the fifth one here, easy to get, so we know all this. We know from the exchange current we can get our K0, or you can do it from you can get this directly from rotating disk experiments on the mediator itself. So we can make sure that 1 over IK is always infinity, so IK is always going to be high. We can set up our experiment to make sure that this is always true. And so we can then focus our engineering efforts on engineering the properties of our membrane and our enzyme reactions. So I do recommend this because it's got inbuilt checks. Is this a linear relationship? If so, we start to believe the result. Do our intercepts scale linearly with concentration of our target? If so, we know we're doing the right experiment. We can get real data out about the kinetics of every single step of our enzyme reaction. So that's the physical scientist's approach to building enzyme sensors. Here's an example of one that we worked on, which with Professor Boutel about 10 years ago, where we were using competing enzyme reactions to get measurements of ATP, the energy currency within cells, by looking at the competition between hexokinase to phosphorylate glucose and glucose oxidase to oxidize glucose, and taking the ratio of these currents, we're able to get reasonable calibration working curves in the micromolar range and measure ATP concentrations in guinea pig gut. So some quite nice stuff arises from these kinds of analyses. A little bit of data analysis, it can go a long way. So every stage of the biosensor design merits deep thought, I would say. The mass transport conditions in the sample, the molecular recognition chemistry that you're going to use, the transduction event that you're going to exploit, and the back of the scenes data analysis. And this was a project where we were wanting to measure neurotransmitters whose formal potentials are really too close to be resolved using cyclic voltammetry, whatever anyone in the literature tells you. You can't really resolve better than 200 millivolt peak potentials in cyclic voltammetry. So we see, but what we did here is we did AC voltammetry, so we apply a large amplitude sine wave modulation on a ramp, and we get these wonderfully rich and quite elegant looking spirograph-like data, as we see over here on the right, that compared with the single peak that we got for the oxidation. And this is model data from cyclic voltammetry. And by fitting these envelopes, we can get some neat experiments using the Hilbert transform. A Hilbert transform is what you have to add to your signal, multiplied by the imaginary number in order to make it an analytic signal. It's like basically a pi over 2 shift. So it's a convolution is the way to think about this. But once you've made the single analytic throughout, by doing this, you can then get the instantaneous amplitude, and you can get the instantaneous frequency from the differential of the phase angle. And this is, we applied this, and in addition to doing a bunch of analysis, we also applied this as a real-time filter on data to separate out dopamine from serotonin. So our raw data shown on the top left here, not very promising looking. We plot the Hilbert transform of this data, of the amplitude, do the Hilbert transform, plot the instantaneous amplitude as a function of time, and we start to see an envelope emerging close to where these two black lines are. We replot this data as versus potential, and we can see one of the envelopes has got 2 peaks in it, and we chose to use this low potential peak, which you don't see in the core amperometric data. We examined this, and over the 1 to 10 micromolar concentration range, we saw a linear relationship between the amplitude of this envelope at the red dot and the concentration of the dopamine, close to 0 volts, so where we get relatively little interference. We then do the same with the serotonin. Again, some fairly flaky looking data, but we see an envelope emerge again very clearly in the bottom left-hand side, which again in the micromolar concentration range scaled with concentration. The magnitude of the fit to this, by fitting a spline to this envelope here, we were able to get concentrations out as shown here. And by optimizing the excitation parameters, we were able to outrun a common interference reaction with ascorbic acid. So we put ascorbic acid in to this solution at concentrations more than 10 times higher, in this case 50 times higher than our target analyte concentration. And when we looked at the, when we optimized this frequency, let's go back to this slide, we could see that at 80 hertz, we were getting no response. So 150 hertz, rather, we're getting no response. The color has changed here. But the 150 hertz excitation gave no response to ascorbic acid and still gave us a dopamine response. So we were able to outrun this reaction by exploiting the differences in kinetics at the transduction event solely by using signal processing. So in the dopamine window, we got no response to serotonin and a pretty good linear response over the range that we were interested in our neurochemistry experiments, which is 0 to 10 micromolar. In the serotonin window, the 5-HT window, we got small response to dopamine, so not perfect, but a much higher response to serotonin, again, in the concentration range that we were interested in. But best of all, we got no signal from ascorbic acid, despite it being present at 2 orders of magnitude higher concentration. We saw no peak for it at all by outrunning it. So that's another approach to selectivity. Going back to cyclic voltammetry, we need to bear in mind a couple of things, just based on things I've seen in the lab and in examining PhDs, is the relationship between the non-Faradaic signal and the Faradaic signal needs to be borne in mind, and this sets absolute limits on what the smallest scan rate is that you can reasonably use. So the minimum scan rates require that the diffusional length scale is smaller than the natural convection boundary layer. So if we take, we're on the sort of anti-penultimate paragraph, the 1/3 from the bottom. The minimum scan rate requires that the diffusional length scale is small compared with the natural convection boundary layer or your Nernst layer. The natural convection boundary layer is typically 5 times 10 to the minus 4 meters, that kind of order. So if you're doing a potential scan of 2 volts, it needs to be over in 100 seconds. Otherwise, you're going to get natural convection distorting your concentration layer, and your voltammograms are not going to be analyzable accurately by the conventional Nicholson-Shane or Randall-Sevcik equations. So that means that your scan rate, if you're doing a volt up and a volt back, your slowest scan rate that's reasonable is 20 millivolts per second. And we can estimate the capacitance from the hysteresis and the double layer, and that's really useful for monitoring adsorption or detection failure. Background subtraction, which is really widely used in the published literature, is completely flaky for any reaction that involves adsorption. Because as your target molecule adsorbs, it will be displacing double layer ions, counter ions, and therefore the background current that you get in the presence of your target will not be the same as the background current that you get in the absence of your target. So we know that double layer structure is going to be affected by the reaction for many of these catecholamines. And the final point I would like to hammer home, because again, this is something I've had to mention to quite a few students over and even postdocs over the years, is that the classic analysis for cyclic voltammetry is only valid for the initial scan. Look at the boundary and initial conditions that Nicholson and Shane used to solve those equations, and you will see that the initial condition is that the analyte concentration is homogeneous for at all points beyond the electrode surface. And that will not be true for your second scan. And how many people say, oh, I did the first scan and I recorded second and subsequent scans and then analyze them? Well, recording second and subsequent scans, fine. There is, in fact, a solution for the steady state one, for infinite scans, going back to the 1950s. You might need to use that, but you cannot use the conventional Nicholson-Shane, Randall-Sevcik equations, which are shown at the top here, if you're not looking at the initial scan. So just bear that in mind as a caveat emptor. Pulse techniques, differential pulse voltammetry. People rule this out because it's slower than square wave voltammetry. But in our hands, we have always found it to be more reliable, more robust, with better limits of detection. And I think if it's going to take you 2 hours to set up the cell, 3 days to build your electrode, spending an extra 10 minutes recording your signal, you know, okay, you're fed up and even 10 minutes seems like a burden, but you know, have a little go at this. And I always urge you to consider these. You get these as simulated data, but you can get pretty good limits of detection with most of these, certainly sub-nanomolar if you run it properly and optimize it. Square waves, the interpulse interval is the same as the pulse length in this. The analysis is super complex. You do need to read the analysis of this in order to do this right. Some lovely papers from Macheski, from the Lovrich group, in other words. And there's a very nice paper from Julie McPherson's group published 3 years ago in Annal Chem, where showing how you can get the double layer capacitance at the same time as your analyte concentration, which is a really nice way of checking if your background subtraction is legitimate. But I would always encourage you to look at the forward curves and the backward curves as well as the differences. And I think it's a great shame that commercial instrumentation doesn't allow you to get the complete current, i.e. the whole response, so you could analyze it yourself. But really, the superb overview by Lovrich, which is a bit of a nightmare and could take you weeks of revisiting it before you start to get to grips with it, but it will really improve your analytical methods. And it's only 12 years old, but this Schultz's Electrochemical Methods, second edition, has got this analysis in, and it really is well worth a look at if you insist on using square wave voltammetry, just to be in with the fashionable crowd that use it everywhere. So, hey, almost on time. My conclusions. The first clause, I think, is the most important conclusion. Biology is difficult. It's complicated. And unlike physics and physical chemistry, there's no underlying deep theory. You just have to get in the lab, do your experiments, do as many experiments as you can, and hope that some shadowy pattern emerges from the mist. It's not like physics, where you say, okay, I've got quantum mechanics, I've got Maxwell's equations, I've got Newton's laws, or relativity if I'm very big or very fast, and I can hang all of my data onto that and I know if I'm going to be right. It doesn't work like that. Biology is at the kind of state that organic chemistry was in the 1890s, before they were certain about what made organic chemicals organic chemicals. I would encourage you, in collaboration with your clinical and biological and life sciences partners, to get a clear definition of the problem, understand the context of the measurement. So this requires you to identify good collaborators, not necessarily the first clinician that comes to talk to you. Talk to several people. Get a sense of the problem. Your core analytical sciences that you may or may not have covered as an undergraduate should inform all of your method development and validation. Do enough control experiments. Use reference methods to validate ideally random samples. Get other people to do your reference analysis for you, so that if you get results back from them that agree with your sensor, you're super confident then that you've done it right. Consider using spike and recovery. Do a realistic estimate of the uncertainty and error propagation. Prepare to be disappointed. And quantitatively define the goals of your method or your device, so that you can do evaluations as whether or not this thing is even working. And the final point is your fundamental electrochemistry and phys chem are going to underpin your method development. It's not enough to hope that you've done the control experiments and rely on statistical methods to back out your results. What we need to be able to do is ideally identify a causal link between what we're trying to quantify and the signals that we get recorded on our computer. And as ever, this was the work of millions. This is a quote from Gulliver's Travels. There's a lovely section where he's satirizing the Royal Society. He wrote this in 1726. And this is a direct quote from one of the scientists that he's satirizing. Young students were employed in this labor, which might still be improved and much expedited if the public would raise a fund. So nothing has changed. The work I was showing today was, of course, not my own. based on some of my mad ideas, but Phil Gillespie, Yuchi Chen, Xiaokai Hong, Xiaotong Meng did some great stuff here. Shulin Zhang, who's not listed here but should be, for the Kutekulevich analysis and the lactate stuff, worked closely with postdoc chemist Dave Freeman, Sally Gowes, great physicians, Tim Rawson, Damien Ming, infectious disease physicians, a wonderful research pharmacist, Richard Wilson, who's run all of our clinical evaluations, great electronics from Manos Drakakis and his PhD student, George. Important and useful collaborations from Tony Cass, Tor Scientific, Professor Alison Holmes in infectious diseases in the med school, and Pantelis Georgiou in electrical engineering, and bundles of money from all of these people listed below. Innovate UK have been very kind to us, the Biomeria Foundation, Medical Research Council, EPSRC, Tor Scientific have coughed up a little bit or provided services. The NIHR has funded some of this work, BBSRC. Japanese drug company Shinogi are paying for one of my PhD students. We're looking at the new antimicrobial cefiderocol for them. And we're very grateful for their continued support for our ideas. What I didn't do, I skipped this slide. I do recommend that you look at this as well. This is where we have found useful information. So reference methods, official and standardized methods analysis by Watson. Consider using analytical abstracts to search for things. Look at the technical briefs of the Royal Society of Chemistry Analytical Methods Committee. They are great for statistical methods. 1 or 2 pages, no more than that. So it's something you can face over a cup of tea or over your lunch as to how to tart up your data and how to handle things properly. Use Web of Knowledge or Web of Science because that's something we pay for. If you're using Google, bear in mind, using Google to do your searches, bear in mind that the search data it will give you back depends on your search history. If you're not the customer, you're the product. There's a reason they're giving this for free. Fundamental reviews of analytical chemistry, which are published annually on different methods, are really, really good. These are invited and critically analyzed. Track is also pretty good, and Crit Rev Analchem is also good. But these annual reviews in Analchem are really highly recommended. And one of the best, Bard and Faulkner, best books, really. Kissinger and Heinemann, the big yellow book, a little out of date now, but has got some great top tips. And there, it's an enormous, great brick of a book. So worst case scenario, if you don't find anything useful in it, you can prop up your experiments with it.